New York has built the most ambitious and over-engineered megaprojects the world has ever seen. From underground tunnel networks to gravity-defying towers, these projects push the limits of money and imagination. Today, we uncover New York's biggest megaprojects and the staggering scale of what it took to reshape one of the most iconic places on Earth. The construction of Hudson Yards, located on the west side of Manhattan, represents one of the most ambitious private real estate developments in the history of the United States. The site, once dominated by an active train yard known as the West Side Yard, posed a formidable engineering challenge due to the need to build over 20 rail tracks in constant operation. The project's realization required a complex orchestration of civil, structural, and mechanical systems in order to create a functional and stable platform that could support multiple high-rise structures while allowing uninterrupted train service beneath. The initial phase of construction centered around the creation of a massive platform, which involved installing approximately 300 caissons. These deep foundation elements, bored between existing rail lines and into the bedrock below, served as vertical supports for the deck that would eventually span the yard. Each caisson was constructed using a combination of drilled shafts reinforced with steel and filled with high-strength concrete, reaching depths of up to 100 feet. Due to the spatial constraints imposed by the active rail operations, each caisson had to be installed with extreme precision using specialized rigs positioned during coordinated windows when train traffic was paused or rerouted. Above the caissons, structural steel grillages and transfer girders were installed to distribute building loads across the uneven geometry of the train yard. These steel elements, many of which weighed in excess of 100 tons, were fabricated off-site and delivered during low-traffic hours to reduce disruptions. Erection of the steel frame platform was carried out using crawler cranes and gantry systems designed to maneuver around the tight constraints of the site. Temporary scaffolding, shoring towers, and falsework were used extensively to stabilize the platform sections during assembly. Once the platform structure was complete, a complex network of utility corridors, ventilation systems, and access points was integrated into the void space between the train tracks and the platform deck. This included active cooling systems designed to dissipate the heat generated by diesel locomotives, as well as fire suppression systems, emergency egress routes, and conduits for electrical and telecommunication lines. Special attention was paid to drainage and water management, as the deck needed to remain impermeable and resistant to both surface runoff and the thermal stresses caused by seasonal freeze-thaw cycles. Simultaneously, vertical construction began above the platform with the erection of high-rise towers featuring both steel and reinforced concrete superstructures. Tower cranes were mounted directly onto the platform and sometimes even cantilevered off the side to accommodate building footprints. For residential and commercial towers, high-strength concrete was pumped from staging areas outside the yard through a series of reinforced pipelines, ensuring consistent quality and flow rate. Core walls, which housed elevators, stairs, and utilities, were slip-formed in a continuous process to accelerate vertical progress and maintain alignment. Curtain wall systems consisting of glass and aluminum panels were fabricated off-site and installed using motorized hoists and mast climbers. These units were engineered to meet stringent performance criteria related to wind loads, thermal insulation, and sound attenuation due to the exposure of the site and its proximity to the Hudson River. The facade systems were also integrated with mechanical louvers and operable components to support the sustainable design targets set for the project. Mechanical, electrical, and plumbing installations were coordinated using building information modeling to avoid clashes and maximize available ceiling space. Centralized utility plants were constructed to serve multiple buildings with chilled water, steam, and power, using a combination of cogeneration and high-efficiency equipment. These plants were interconnected through a network of underground tunnels and risers, carefully designed to minimize energy loss and facilitate future maintenance access. Interior build-outs varied depending on occupancy type, but generally involved raised access floors, demountable partition systems, and state-of-the-art fire protection and life safety systems. For the retail podium, load-bearing transfer slabs were installed to accommodate large open floor plans and dynamic occupancy loads. This required the use of high-performance concrete with additives that enhanced pumpability and cured strength, particularly for spans exceeding 50 feet. Public realm elements, including the plaza and landscaping above the platform, were constructed using a layered assembly that included structural foam, drainage mats, root barriers, and engineered soil. These layers supported a diverse range of plantings, pedestrian pathways, and stormwater retention features. Custom-designed tree pits and planters were built into the deck slab, allowing mature trees to thrive despite limited soil depth and exposure to wind shear. Throughout the construction process, logistics were a primary concern, as the confined urban site required just-in-time delivery scheduling, off-site staging areas, and constant coordination with city agencies and transit authorities. Noise and vibration monitoring, environmental controls, and dust suppression systems were continuously deployed to minimize impacts on neighboring communities and infrastructure. The overall success of Hudson Yards was underpinned by an integrated project delivery model, which relied on collaboration among architects, engineers, contractors, and stakeholders from the earliest planning stages. This level of integration allowed for accelerated construction timelines, efficient risk mitigation, and optimized resource use, culminating in the completion of a new urban neighborhood that seamlessly integrates infrastructure, real estate, and public space atop an active rail yard. The construction of the East Side Access Project in New York City is one of the most complex and technically challenging transit undertakings in the history of the United States. Designed to connect the Long Island Railroad to a new terminal beneath Grand Central Terminal in Manhattan, this massive infrastructure project required the excavation of multiple tunnel systems, the construction of subterranean caverns, and the integration of entirely new rail systems within one of the most densely built environments in the world. Spanning decades of planning and construction, the project unfolded deep beneath the city's surface, demanding extraordinary precision and coordination across multiple engineering disciplines. At the core of the East Side Access Project was the tunneling phase, which involved the excavation of nearly 15 miles of new tunnels beneath Queens and Manhattan. This began with the deployment of tunnel boring machines, each weighing hundreds of tons and extending over 400 feet in length. These machines were launched from access points in Queens and advanced westward under the East River through soft ground and bedrock. To maintain stability in varying geological conditions, different TBM technologies were employed, including earth pressure balance and slurry shield methods. The TBM simultaneously excavated and installed precast concrete segmental liners, forming a continuous circular tunnel as they progressed. Each tunnel required continuous monitoring of ground movement, with real-time data collected from instruments embedded in the surrounding soil and rock. Ground stabilization techniques such as ground freezing and jet grouting were employed where necessary to prevent subsidence and protect adjacent infrastructure. Spoil material from the excavation was transported via conveyor belts and muck trains to designated removal sites, where it was processed and disposed of according to environmental regulations. Once the primary tunnels were completed, work shifted to the construction of the Manhattan Caverns, which would house the new terminal platforms and tracks. Located approximately 100 feet below street level, these caverns were excavated using the controlled drill and blast method. Each blast was carefully calculated to fracture rock without damaging existing subway lines and utilities above. The excavated spaces were then stabilized using rock bolts, shotcrete, and steel ribs, followed by waterproofing membranes and reinforced concrete linings. The new terminal complex beneath Grand Central was designed as a bi-level structure featuring 4 platforms and 8 tracks. The layout included numerous cross passages, ventilation shafts, and emergency egress corridors. Each level was constructed with reinforced concrete floor slabs supported by massive girders and columns, engineered to distribute loads uniformly across the cavern walls and foundations. Structural steel framing was used extensively in mezzanine and concourse areas to allow for open spaces and flexibility in architectural finishes. A major component of the East Side Access Project was the installation of a complex track and signal system. This involved laying continuously welded rail on concrete ties set in ballastless track beds, designed for durability and low maintenance. The track alignment required precision to meet curvature and grade requirements, particularly as the trains transitioned from tunnel approaches into the terminal. Overhead catenary systems were replaced by a third rail electrification system compatible with Long Island Railroad rolling stock, necessitating the integration of new power substations and switching equipment. Advanced signal and train control systems were installed, including communications-based train control to enhance capacity and safety. These systems required extensive cabling, signal houses, and testing to ensure interoperability with the existing rail network. Fiber optic communication networks were also laid throughout the tunnels and terminal areas to support operational control and real-time monitoring. Vertical transportation was another critical aspect, given the significant depth of the terminal. High-capacity escalators, some extending over 90 feet in length, were installed to move passengers efficiently between the mezzanine and platform levels. Additionally, multiple banks of high-speed elevators were constructed to provide accessibility and redundancy. Mechanical rooms housing air handling units, chillers, and backup power systems were strategically located throughout the terminal to support passenger comfort and operational resilience. In Queens, the Harold Interlocking, one of the busiest rail junctions in the country, had to be completely reconfigured to accommodate new track alignments for East Side access. This required the installation of new flyovers, viaducts, and switches, while maintaining uninterrupted train service for Amtrak and the Long Island Railroad. Work in this area was conducted in multiple phases, involving track outages scheduled years in advance and executed with military precision. New signal towers and interlockings were built to streamline train movements and improve operational flexibility. The LaGuardia Airport redevelopment project in New York City was an extensive modernization effort aimed at transforming one of the most outdated major airports in the United States into a state-of-the-art transportation hub. The redevelopment involved the complete demolition and reconstruction of Terminals B and C, the building of new roadways and taxiways, installation of modern baggage handling and screening systems, and the integration of advanced mechanical and electrical infrastructure, all executed while maintaining full airport operations. Spanning over 800 acres, the project required innovative construction techniques and phased implementation to address the logistical complexities of building in a fully operational airfield. Initial site preparation for the redevelopment began with extensive demolition work, including the removal of obsolete terminal structures, parking garages, and auxiliary buildings. This phase also involved extensive utility relocation, as critical services such as electrical power, natural gas, potable water, sewer lines, and telecommunications had to be rerouted to maintain service continuity. In addition, environmental remediation was carried out in accordance with regulatory standards, including soil testing and removal of any contaminated material. One of the most challenging engineering aspects of the project was the construction of the new Terminal B, while the old terminal remained operational. To achieve this, the new head house, which would serve as the central terminal building, was constructed in phases. A steel superstructure was erected on deep foundations comprised of driven piles reaching down to bedrock. The pile caps and grade beams formed a stable base for the vertical elements of the building. Structural steel framing was then installed, including long-span roof trusses to support the expansive check-in and baggage claim areas. The use of prefabricated components helped accelerate construction while reducing on-site labor intensity. A distinctive feature of the new terminal layout was the use of dual pedestrian bridges spanning active aircraft taxiways. These bridges connect the head house to two island concourses and are constructed of steel box girders and reinforced concrete decking. They were erected using balanced cantilever techniques with temporary supports and tensioning systems to maintain stability during installation. Each bridge was designed to maintain a clearance height sufficient for Group 3 aircraft to pass beneath, requiring precise survey and alignment coordination. Airside construction included the development of new aircraft aprons, gates, and taxi lanes. This required excavation and grading to achieve proper slope and drainage, followed by the installation of sub-base layers, geotextiles, and Portland cement concrete pavement. Aircraft-rated pavement thicknesses were designed based on expected load distribution from narrow-body and wide-body aircraft. Jet blast fences and visual guidance systems were integrated into the apron design to ensure safety during aircraft movement. On the land side, new roadways were constructed to streamline vehicular access to the terminals. These roads featured elevated and at-grade sections built using cast-in-place concrete and precast segments. Foundations for elevated roadways included drilled shafts and pile-supported abutments. Traffic was managed using temporary detours and signage, while new bridges and ramps were staged to avoid interfering with ongoing operations. Interior construction of the new terminals prioritized modularity and flexibility. Raised access floors allowed for the distribution of power and data cables, while mechanical systems were suspended in accessible ceiling plenums. HVAC systems used air handlers with variable air volume controls, connected to a central chiller plant for efficient cooling. Advanced fire suppression systems, including wet pipe sprinklers and clean agent suppression in sensitive areas, were coordinated through 3D modeling to avoid conflicts with structural and mechanical elements. The baggage handling system represented a critical logistical element, comprising miles of conveyor belts, automatic sorters, and explosive detection systems. These were installed in stages, with integration and testing conducted in tandem to ensure seamless operation. The entire system was monitored by a centralized control room equipped with diagnostic tools for system performance and fault detection. Electrical infrastructure included the installation of new substations, switchgear, and emergency backup generators. Redundancy was built into the power supply network to ensure uninterrupted service to terminal systems. Lighting throughout the terminal employed LED fixtures with daylight harvesting controls, while building management systems monitored energy consumption, air quality, and equipment status. Sustainability played a significant role in the design and construction process. The terminal buildings incorporated high-performance glazing, green roofs, and low-flow plumbing fixtures to reduce environmental impact. Stormwater management features included bioswales, underground detention basins, and oil water separators to treat runoff before discharge. The construction team adopted a design-build-delivery method to streamline coordination between contractors and designers, enabling faster decision-making and reducing change orders. Coordination was further enhanced through the use of building information modeling, which allowed multidisciplinary teams to resolve conflicts virtually before beginning physical work. Weekly progress reviews, safety audits, and schedule updates ensured that construction proceeded according to plan despite the dynamic nature of the airport environment. The Javits Center expansion project in New York City was a transformative construction endeavor that significantly increased the capacity and functionality of the Jacob K. Javits Convention Center, one of the largest such facilities in the northeastern United States. The expansion added more than 1 million square feet of space, including exhibit halls, meeting rooms, a rooftop pavilion, and a state-of-the-art truck marshaling facility. Executed on a constrained urban site adjacent to the Hudson River and operating rail lines, the project required a combination of advanced structural engineering, phased logistics, and sustainability-driven design. The initial phase of the project focused on extensive site preparation. This involved clearing the western portion of the existing property, relocating underground utilities, and driving piles for the building foundation. The ground conditions included fill material and soft soils, necessitating the use of deep foundation systems. Steel H-piles were driven to refusal into glacial till and bedrock to support the new superstructure. These piles were then capped with reinforced concrete pile caps interconnected by grade beams, forming a stable platform for vertical construction. The expansion superstructure was designed using a steel frame system, chosen for its strength-to-weight ratio and speed of erection. The main exhibition hall required long-span roof trusses capable of supporting overhead rigging loads for events while providing a column-free interior. These trusses were assembled on-site and lifted into place using crawler cranes with high lifting capacity. The structural steel frame included moment-resisting connections to resist lateral loads from wind and seismic forces, supplemented by braced frames where architectural design permitted. The exterior envelope of the building was constructed using a unitized curtain wall system featuring high-performance glass and aluminum framing. The glass panels were fabricated with low emissivity coatings and frit patterns to control solar gain and reduce glare within the exhibition spaces. The building envelope also incorporated insulated metal panels and rain screen cladding, supported by subgirts attached to the structural frame. A continuous air barrier and vapor retarder were integrated behind the facade to ensure thermal performance and prevent moisture intrusion. One of the central features of the expansion was the truck marshaling facility. which included 4 levels of enclosed, climate-controlled space designed to accommodate up to 200 trucks. This facility was constructed using post-tension concrete slabs supported by concrete columns and shear walls. The structural system was engineered to carry heavy live loads and included clear spans and high ceilings to facilitate truck maneuvering. A vehicle guidance system was installed to optimize truck flow and minimize idling times. Vertical transportation throughout the expanded center was provided by multiple banks of elevators and escalators. Freight elevators with oversized cabs and high load ratings were installed to move large exhibits and equipment between levels. Passenger elevators and escalators were placed in high-traffic areas to support efficient movement of attendees and staff. All systems were integrated into a building-wide control system for monitoring and maintenance. Mechanical, electrical, and plumbing systems were designed to meet the demands of large-scale events. Air handling units were placed on mechanical floors and connected to a network of ductwork, with variable air volume boxes to provide zoning control. Chilled water and heating hot water were supplied from a central energy plant using high-efficiency chillers, boilers, and heat exchangers. Building automation systems controlled temperature, humidity, and ventilation in real time. Electrical distribution included new switchgear, step-down transformers, and emergency power via diesel generators and uninterruptible power supplies. The expansion also included a rooftop pavilion and terrace which doubled as a green roof and outdoor event space. This area was built using lightweight structural systems to reduce loading on the roof deck and included pavers on pedestal supports, planting beds, and integrated lighting. Stormwater runoff from the roof was captured and stored in underground cisterns for non-potable reuse, such as irrigation and cooling tower makeup water. Photovoltaic panels were installed to contribute renewable energy and offset utility consumption. Interior construction of the exhibition and meeting spaces emphasized durability, flexibility, and acoustic performance. Raised floors were used in selected areas to allow for reconfigurable power and data connections. Operable partitions divided large meeting rooms into smaller breakout spaces, with acoustic insulation to minimize sound transfer. Finishes included terrazzo, carpet tile, and gypsum board with high recycled content, all selected to meet LEED certification criteria. A major component of the construction effort was the integration of the expansion with the existing Javits Center. This required selective demolition of exterior walls and structural elements, followed by tie-ins to existing mechanical and life safety systems. Phased construction ensured that the existing facility remained operational throughout the project. Temporary partitions, rerouted utilities, and interim egress paths were deployed to maintain safety and functionality. The construction of One Vanderbilt, a super-tall skyscraper located adjacent to Grand Central Terminal in Midtown Manhattan, involved a highly complex sequence of engineering, structural, and logistical operations. Rising to a height of over 1,000 feet, One Vanderbilt integrates advanced construction techniques and urban transit improvements into a single vertical development, setting a new benchmark for commercial office towers in densely built environments. The project demanded meticulous planning and coordination, particularly given its proximity to historic structures, active transit infrastructure, and high pedestrian traffic zones. Site preparation began with the demolition of several pre-existing mid-rise buildings. This process involved asbestos abatement, structural dismantling, and foundation removal. Due to the tight urban footprint and adjacent properties, much of the demolition was carried out using high-reach excavators and hydraulic breakers rather than traditional implosion or large-scale mechanical demolition. Once the site was cleared, excavation commenced for the new foundations, which reached over 60 feet below grade to accommodate the tower's deep basement levels and the integration of a new transit hall connecting to Grand Central Terminal. Subsurface conditions required the use of slurry wall construction to provide lateral earth support during excavation. A perimeter slurry wall, composed of reinforced concrete panels formed within bentonite-supported trenches, was installed to retain surrounding soils and water. Tiebacks and internal bracing were employed to ensure wall stability as excavation advanced. Excavated material was removed using conveyor belts and dump trucks, with loads scheduled during off-peak hours to minimize traffic disruption. The foundation system consisted of a combination of spread footings and deep caissons drilled into bedrock. The caissons, some exceeding 6 feet in diameter, were constructed using large rotary drilling rigs and reinforced with steel cages before being filled with high-strength concrete. These elements were designed to transfer the enormous vertical loads from the tower into the Manhattan schist below. A thick matte foundation slab was poured over the caissons, utilizing thousands of cubic yards of concrete delivered in a continuous 24-hour operation. The superstructure of One Vanderbilt utilized a composite structural system combining a reinforced concrete core with structural steel framing. The core, which houses elevators, stairs, and mechanical risers, was constructed first using slip-form technology. This technique involved the continuous pouring of concrete into a moving formwork system, allowing rapid vertical advancement. The core served as the backbone of the building, providing torsional resistance and lateral stability. Around the core, structural steel beams and columns were erected to form the building's floor framing. High-strength bolted and welded connections linked the steel elements, while metal decking and concrete topping slabs formed the composite floor systems. The building's tapering profile and multiple setbacks required specially fabricated steel members and custom connection details. Each steel floor was erected using tower cranes positioned within the core, later climbed to upper levels as the building rose. To achieve the building's slender profile and withstand wind loads, One Vanderbilt incorporated tuned mass damping systems at its upper levels. These systems consist of massive weights suspended and supported by hydraulic or spring systems, which counteract building sway during high wind events. The structural engineers also designed a system of outrigger trusses and belt trusses that tied perimeter columns to the central core, distributing lateral forces more efficiently and enhancing overall rigidity. The curtain wall system featured unitized glass and aluminum panels that were pre-assembled and tested off-site for quality and performance. Each panel included insulated glazing units with solar control coatings, contributing to the building's energy efficiency. The panels were hoisted into place using monorail rigs and suction equipment mounted to floor slabs, with careful alignment to ensure thermal and air barrier continuity. Integrated ventilation louvers and operable windows provided occupant comfort and facilitated natural airflow. Mechanical systems for One Vanderbilt were designed for high performance and tenant flexibility. The building was served by multiple mechanical floors housing chillers, air handling units, and water pumps. The chilled water system used high-efficiency centrifugal chillers with variable frequency drives, connected to fan-powered terminal units distributed throughout tenant spaces. The vertical distribution of mechanical services was handled through stacked mechanical shafts integrated within the core. Electrical infrastructure included redundant feeders from the utility grid, emergency diesel generators, and automatic transfer switches to ensure uninterrupted service. Advanced building management systems controlled lighting, HVAC, and security systems with sensors deployed to monitor occupancy and optimize energy use. High-capacity risers for telecommunications, data, and security cabling were installed to accommodate diverse tenant requirements. Vertical transportation consisted of over 40 elevators divided into zoned banks, some of which utilized destination dispatch technology to minimize wait times and energy use. Express elevators connected lower floors to sky lobbies, while service elevators were designed with extra depth to handle large tenant equipment and furniture. At the base of the tower, a new transit concourse was constructed to improve access to Grand Central Terminal and the subway lines beneath it. This involved underpinning sections of the historic terminal structure and constructing new passages, escalators, and ticketing areas. Complex waterproofing systems, including bentonite mats and integral water stops, were installed to protect the subterranean spaces from groundwater intrusion. Public realm improvements included widened sidewalks, landscape plazas, and an open-air pedestrian corridor that created visual and physical connections to Grand Central Terminal. Paving, lighting, and street furniture were coordinated to enhance pedestrian circulation and safety. The redevelopment of Penn Station in New York City is a large-scale infrastructure and architectural initiative designed to transform one of the most heavily trafficked and functionally outdated transportation hubs in the United States into a modern, efficient, and passenger-focused facility. This multifaceted project involves the complete overhaul of existing station elements, integration of new transit connections, and the construction of Moynihan Train Hall as an extension of Penn Station's operational footprint. The redevelopment process unfolded across multiple phases, each requiring intense coordination between civil, structural, mechanical, and transportation engineering disciplines, all while maintaining continuous transit service for hundreds of thousands of daily commuters. The first critical step in the redevelopment was the structural conversion of the James A. Farley Post Office building into the new Moynihan Train Hall. This Beaux-Arts structure, located directly west of Penn Station, was originally constructed with massive granite walls and steel floor framing. Adapting this historic facility to serve as a modern rail terminal required surgical demolition of interior structural elements and the reinforcement of floor slabs and columns to accommodate new loading requirements. The most dramatic transformation occurred with the installation of a vaulted steel and glass skylight system over the former mail sorting room, now repurposed as the main concourse. This skylight was supported by new structural steel arches tied into the existing steel framing through moment-resisting connections. The entire installation had to be designed to accommodate differential settlement, thermal expansion, and seismic movement. Beneath the concourse, platforms and tracks serving Amtrak and Long Island Railroad were upgraded to meet modern standards. This involved improving vertical circulation with new escalators and elevators, reinforcing platform edges, upgrading lighting, signage, and wayfinding systems, and integrating accessibility features in compliance with the Americans with Disabilities Act. The mechanical ventilation systems serving the platforms were also expanded, including the installation of new fans, air shafts, and smoke evacuation ducts. The expansion of concourse areas continued under the streets and buildings adjacent to the existing Penn Station, where new subterranean pedestrian corridors were excavated using a combination of cut and cover and hand mining techniques. These corridors were lined with waterproof concrete and outfitted with finishes that matched the aesthetic of the new train hall. Special care was taken during excavation to protect nearby building foundations and subway infrastructure, employing instrumentation to monitor ground movement in real time. Within the original Penn Station footprint, structural retrofits were carried out to open up the low-ceilinged areas that had long hindered passenger flow and visibility. This included the removal of non-structural mezzanines and drop ceilings, the relocation of HVAC ductwork, and the replacement of outdated mechanical systems. Load-bearing columns were clad with fire-rated materials, and floors were refinished with terrazzo and stone tile to improve durability and appearance. Lighting systems were upgraded to high-efficiency LED arrays, integrated with motion sensors and daylight harvesting controls. A new entrance pavilion was constructed on 7th Avenue, creating a prominent street-level presence for the station. The pavilion consisted of a steel-framed structure with a glass facade supported by tensioned cable trusses. This open and transparent design brought natural light into the concourse and served as a visual counterpoint to the previously closed-off street frontage. Beneath the entrance, new circulation stairs, escalators, and elevators were installed to move passengers from street level to concourse and platform levels with minimal congestion. Mechanical, electrical, and plumbing systems throughout the redeveloped station were completely overhauled. Central utility plants were upgraded with high-efficiency chillers, boilers, and air handling units. These systems were connected to a distributed network of variable air volume boxes and demand-controlled ventilation points designed to adapt to occupancy loads in real time. Electrical distribution was modernized with new substations, transformers, and switchgear capable of supporting expanded digital signage, surveillance systems, and tenant loads. All systems were tied into a centralized building management system with touchscreen controls, alarms, and energy monitoring capabilities. The redevelopment also emphasized sustainability, with features such as green roofing, stormwater management systems, and low-impact construction materials. Green roofs were installed atop portions of the Moynihan Train Hall and the new entrance pavilion, supported by reinforced roof slabs and integrated drainage systems. Stormwater runoff was directed to underground detention tanks and treated before being discharged or reused for non-potable applications such as irrigation. During the course of construction, maintaining uninterrupted train service remained a top priority. Work was scheduled in off-peak hours and overnight shifts to limit disruptions. Temporary barriers, rerouted access paths, and detailed construction phasing plans allowed contractors to isolate active work zones from public areas. Safety was ensured through real-time coordination with Amtrak, Long Island Railroad, and New Jersey Transit, with flagging crews and communication protocols in place for track-level activities. Coordination with existing infrastructure was another critical component of the project. Penn Station interfaces with subway lines, path trains, and multiple street-level transportation systems. The redevelopment included improvements to subway entrances, ticketing areas, and passageways connecting the transit systems. Structural ties were established between the old and new facilities, with seismic joints and expansion joints incorporated to account for differential movement between the structures. The Hudson Tunnel Project, part of the broader Gateway program, represents one of the most critical infrastructure efforts in the northeastern United States, designed to create a new two-track rail tunnel beneath the Hudson River connecting New Jersey to Manhattan. This massive undertaking involves constructing an entirely new tunnel system, rehabilitating the existing North River tunnels, and upgrading related infrastructure to enhance capacity, reliability, and resiliency for Amtrak and New Jersey Transit operations. Given the complexity of tunneling beneath a river in a densely urbanized corridor, the project requires advanced geotechnical planning, innovative construction methodologies, and rigorous logistical coordination. The construction of the new Hudson Tunnel begins with the establishment of tunnel portals on both the New Jersey and Manhattan sides. On the west side, in North Bergen, site preparation includes clearing a large staging area, relocating utilities, and driving deep foundations for the tunnel entrance structure. This involves the use of soldier piles and lagging systems to create excavation support for the open-cut sections of the tunnel approach. The excavation is conducted in phases, with groundwater control measures such as weld points and deep wells installed to stabilize the soil and lower the water table. On the Manhattan side, the tunnel emerges beneath Hudson Yards, requiring intricate coordination with existing foundations, utilities, and operational rail infrastructure. Access shafts and launch boxes are constructed using slurry wall and secant pile techniques to create watertight enclosures. These structures serve as both tunnel access points and critical infrastructure for ventilation and emergency egress. Dewatering systems and continuous monitoring are essential throughout the excavation process to prevent settlement or structural damage to nearby buildings. The main tunnel drive is carried out using pressurized face tunnel boring machines, or TBMs, specially designed to operate in mixed face conditions comprising soft soils, silts, and bedrock. Each TBM is equipped with a rotating cutter head, shield, and trailing support systems that handle spoil removal, segment installation, and auxiliary systems. The TBMs are launched from the New Jersey side, advancing eastward beneath the Palisades, the Hudson River, and into Manhattan. As the machines progress, they install precast concrete segments to form the tunnel lining. Each ring comprises several curved segments with waterproof gaskets bolted and grouted in place to create a continuous sealed tunnel shell. Spoil material generated by the TBMs is transported via conveyor belts or muck trains to the portal areas for removal and disposal. The tunnel boring process is carefully monitored using automated systems that track TBM position, face pressure, cutter wear, and ground movement. Data is relayed to control rooms where engineers can adjust parameters in real time to optimize performance and mitigate risks. Once the twin bores are completed, a range of secondary construction activities takes place inside the tunnels. This includes the installation of track bed systems, drainage lines, utility conduits, and concrete walkways. A concrete invert is poured to create a flat surface for ballastless track systems, typically slab track, which ensures high-speed stability and reduced maintenance. Third rail or overhead catenary supports are anchored to the tunnel lining, depending on the electrification method used. Signal cable trays, fiber optic communication lines, and fire detection systems are integrated along the tunnel interior. Mechanical and electrical systems include powerful ventilation fans housed in dedicated shafts, designed to maintain air quality during regular operations and to evacuate smoke in the event of fire. Emergency lighting, evacuation signage, and public address systems are installed throughout the tunnels, with cross passages between bores spaced at regular intervals to facilitate emergency egress and firefighting access. At each tunnel portal, substations and switchgear are constructed to supply power to trains and tunnel systems. These facilities include redundant transformers, switchboards, and backup power sources such as diesel generators and uninterruptible power supplies. The entire tunnel is connected to a centralized control system that monitors train movement, environmental conditions, and system performance in real time. Simultaneously with the construction of the new tunnel, the project involves the future rehabilitation of the existing North River tunnels, which suffered saltwater damage during Hurricane Sandy and continue to degrade. Once the new tunnel is operational, rail traffic will be rerouted through the new bores, allowing the old tunnels to be taken offline sequentially for full restoration. This process includes the removal of deteriorated track systems, replacement of corroded bench walls, structural repairs to the concrete liner, installation of modern waterproofing membranes, and upgrades to all mechanical and electrical systems. The Hudson Tunnel project also incorporates track realignments and yard reconfigurations on both sides of the river. In New Jersey, additional work includes the construction of approach structures and flyovers to integrate the new tunnel into existing Amtrak and NJ transit lines. In Manhattan, the connection involves carefully threading the new tracks into Penn Station's complex and congested rail throat. This necessitates new signal interlockings, turnout installations, and extensive coordination with other rail improvement projects in the area. Environmental mitigation measures are implemented throughout construction to protect water quality, air quality, and adjacent ecosystems. These include sediment control barriers, air filtration for construction sites, and noise suppression systems. Special consideration is given to minimizing disruption to local communities and existing transportation networks. The construction of the new Highmark Stadium in Orchard Park, New York, the future home of the Buffalo Bills, involves the development of a modern open-air sports facility designed to enhance fan experience, operational efficiency, and long-term durability in a region known for its severe winter conditions. This multi-year, multi-billion-dollar project is being built adjacent to the existing stadium, allowing uninterrupted use of the current facility during construction. The project requires extensive coordination of site development, structural engineering, vertical construction, mechanical systems, and logistics in order to deliver a stadium suited for National Football League operations and year-round community use. The site work began with extensive geotechnical surveys and soil borings to determine subsurface conditions. Given the clayey soils and shallow groundwater common in the region, the stadium's foundation system was designed to include deep foundations consisting primarily of driven steel piles and reinforced concrete drilled piers. These foundation elements extend to layers of dense till or weathered bedrock to ensure settlement control and resistance to frost heave, a key concern in the region's freeze-thaw cycles. Foundation work also included pile caps and grade beams, which tied together vertical loads from superstructure columns and distributed them into the subgrade. Following earthwork and foundation construction, the stadium's structural system began rising from the ground. The primary vertical and lateral force-resisting systems are composed of structural steel frames using wide flange beams, box columns, and truss members to accommodate large spans over seating bowls and concourse levels. Erection of steel components was carried out using crawler cranes, mobile tower cranes, and temporary bracing towers to stabilize elements until permanent connections were completed. Bolted connections predominated for speed and ease of assembly, with some welded joints required for moment-resisting frames in the main concourse and canopy structures. The stadium features a continuous seating bowl with multiple tiers, supported by cast-in-place concrete raker beams and precast concrete treads and risers. These structural components were manufactured off-site and trucked in for installation, using heavy-duty lifting equipment. Precast elements were aligned and shimmed into place, then grouted and anchored to ensure a rigid connection to the supporting steel or concrete framework. Vomitories, stairs, and circulation corridors were integrated into the bowl structure, incorporating slip-resistant coatings and embedded tactile strips for accessibility compliance. A prominent feature of the stadium is its canopy structure. which is designed to cover a significant portion of the spectator seating while remaining open at the field level. The canopy is supported by long-span cantilevered trusses projecting from the outer edge of the upper seating bowl. These trusses were fabricated in segments and lifted into position, then post-tensioned to reduce deflection and improve load transfer. The canopy cladding includes metal panel systems and translucent roofing materials to allow natural light penetration while providing shelter from rain and snow. Snow load considerations were a primary design constraint, requiring robust framing and drainage systems to prevent ice accumulation and structural overstress. Mechanical systems within the stadium include air handling units, hydronic heating systems, and ventilation equipment tailored to the open-air nature of the venue. Large mechanical rooms were installed beneath the seating bowl and in service cores, housing boilers, pumps, and fan systems. Given the region's cold climate, radiant heating systems were embedded into portions of the concourses and key field-level areas to prevent freezing and ensure operational continuity. The field itself incorporates a subgrade heating system to prevent turf freezing and ensure safe playing conditions during late season and playoff games. Electrical systems included high-capacity feeders, switchgear, and lighting panels distributed through electrical closets and conduits hidden within wall cavities and floor trenches. LED lighting systems were installed throughout the stadium, including field lighting, which was mounted on the canopy structure to provide even illumination with minimal glare. Emergency power systems, including diesel generators and battery-backed UPS systems, ensure continuity of life safety and broadcast operations during outages. The stadium's vertical circulation is supported by escalators, elevators, and wide staircases, designed to handle rapid ingress and egress of over 60,000 spectators. Vertical cores were constructed using reinforced concrete shear walls with embedded elevator guide rails and MEP chaseways. All passenger elevators were installed with regenerative drives and machine roomless technology to reduce energy use and maintenance demands. Within the stadium envelope, premium seating areas, suites, clubs, and press facilities were constructed using structural framing and high-end interior finishes. These spaces included raised access floors, custom millwork, acoustic ceiling systems, and advanced audiovisual integration for real-time data display and broadcast capabilities. Extensive mechanical zoning and separate air handling units were used to isolate VIP areas from general circulation zones. On the exterior, the stadium design incorporates architectural metal panels, stone veneer, and curtain wall glazing in key entry points. Exterior plazas and arrival zones were constructed with reinforced concrete pavement, pavers, and landscape features, including stormwater planters and snow melt systems embedded in walkways. Security measures such as bollards, surveillance systems, and controlled entry points were coordinated with structural and civil design. Logistics played a central role throughout the construction process. Given the tight construction schedule, materials were procured using just-in-time delivery methods with on-site laydown areas minimized through advanced planning. Winter construction required temporary enclosures, heated work areas, and cold weather concrete practices, including admixtures and thermal blankets. The construction of One Manhattan Square, a luxury residential skyscraper located on the Lower East Side of Manhattan, required a carefully orchestrated approach to high-rise construction on a waterfront site with challenging geotechnical conditions and limited staging space. Rising over 800 feet in height, the tower features a slender profile and houses hundreds of residential units above a multi-level podium. The project involved extensive subsurface work, a reinforced concrete structural system, curtain wall facade installation, and the integration of extensive mechanical, electrical, and plumbing systems, all within the constraints of a dense urban environment. The first phase of construction focused on site excavation and foundation work. Given the site's proximity to the East River, groundwater management and soil stabilization were critical. Deep excavation was necessary to reach suitable load-bearing strata and accommodate below-grade parking and service levels. A perimeter slurry wall system was constructed to support the excavation and act as a long-term waterproofing barrier. This involved trenching around the site's perimeter, supporting the trench walls with bentonite slurry, and placing reinforcement cages followed by tramy concrete pours to form continuous wall panels. Within the slurry wall enclosure, mass excavation was conducted down to the foundation level. Dewatering systems using well points and sump pumps controlled groundwater intrusion, and real-time monitoring ensured excavation stability. The building's foundation consisted of a thick, reinforced concrete mat slab, designed to distribute vertical loads across the footprint while resisting hydrostatic uplift pressure. The mat was poured in large segments using high-strength concrete with admixtures to enhance durability and control curing. Vertical construction proceeded with the erection of a cast-in-place reinforced concrete superstructure. The building's structural system was composed of a central concrete core housing elevators, stairs, and mechanical risers, surrounded by perimeter columns and shear walls. The core was constructed using a jump form system, allowing continuous vertical progress while floor slabs were cast around it using flying formwork and table forms. Each floor cycle averaged several days with rebar post-tensioning cables and mechanical sleeve penetrations installed prior to concrete placement. High-strength concrete mixes were used to achieve the design compressive strength required for slender tower stability. Lateral loads from wind and seismic activity were resisted primarily by the stiffness of the core and the interaction of shear walls distributed along the tower's footprint. To reduce construction time, climbing formwork systems and tower cranes were deployed to support material delivery and personnel movement as the building rose. The tower's facade system featured a unitized curtain wall assembly composed of aluminum frames and insulated glass panels with low emissivity coatings. Each panel was fabricated off-site, pre-glazed, and tested for air and water infiltration before delivery to the site. Curtain wall installation occurred concurrently with structural work, with panels hoisted into position and anchored to embedded inserts at slab edges. The panels also included spandrel sections to conceal floor slabs and mechanical systems, providing a continuous visual envelope. Mechanical, electrical, and plumbing systems were routed vertically through dedicated shafts within the core and extended horizontally across each floor plate. The building's HVAC system relied on fan coil units and centralized chillers located in mechanical floors, supported by rooftop equipment and condenser water loops. Fresh air intake and exhaust systems were integrated into the facade using hidden louvers and custom architectural details. Plumbing systems were zoned by floor and included pressure-boosting pumps and backflow prevention devices to maintain consistent service across all levels. Electrical systems included dual utility feeds, on-site transformers, and emergency backup generators. Sub-metering was implemented to track usage by individual residential units, and distribution panels were installed in closets on each floor. Fire protection systems consisted of wet pipe sprinkler systems, standpipes, and fire alarm wiring, all coordinated using building information modeling to avoid conflicts with structure and finish systems. Interior fit-out began once the building envelope was enclosed and permanent power was established. Each residential unit featured gypsum board partitions, sound-rated floor assemblies, and high-end finishes including wood flooring, custom cabinetry, and stone countertops. Kitchens and bathrooms were prefabricated as modular assemblies where possible to accelerate installation and improve quality control. Energy-efficient appliances, LED lighting, and smart home technology were integrated into the units. Amenity spaces were constructed within the building's podium and included fitness areas, lounges, spa facilities, and entertainment rooms. These spaces required specialized mechanical zoning and sound isolation to provide acoustic comfort and performance. Finishes in these areas included acoustic ceilings, soft flooring, and decorative lighting systems. An exterior landscape terrace was built over the podium roof slab, incorporating lightweight fill, waterproofing membranes, and stormwater management features such as planters and drainage mats. Vertical transportation systems included high-speed elevators equipped with destination dispatch technology to reduce wait times and improve traffic flow. Elevator shafts were constructed using slip-form techniques within the core, and guide rails, cabs, and control systems were installed once the structure topped out. Life safety systems were interconnected through a central command center, with emergency lighting, public address systems, and integrated surveillance and access control equipment. Throughout construction, logistics were tightly controlled due to the site's urban setting. Deliveries were scheduled in narrow windows, materials were staged just in time, and vertical hoists and cranes were used to reduce on-site clutter. Coordination with city agencies ensured that street closures, utility connections, and construction access points were managed without disrupting surrounding traffic and pedestrian activity. The Bronx Point development is a transformative mixed-use project situated along the Harlem River waterfront in the South Bronx. Designed to anchor the revitalization of the Lower Concourse neighborhood, this project blends residential housing, public open space, cultural institutions, and retail infrastructure into a cohesive, community-oriented development. The construction of Bronx Point required a multifaceted engineering approach to address floodplain conditions, brownfield remediation, vertical building systems, and public realm integration on a complex site once used for industrial and municipal purposes. Site preparation began with environmental remediation, as the location was designated a brownfield due to prior industrial use. This involved soil excavation, off-site disposal of contaminated material, and capping of subgrade layers with engineered fill. To stabilize the site for vertical construction, deep foundations were required due to weak soils and the site's location in a designated flood zone. Pile driving commenced using steel H-piles and mini-caissons, reaching down to competent load-bearing strata. Pile caps and grade beams were poured to support the superstructure and resist hydrostatic pressure. Given the site's flood-prone nature, the ground floor of the development was elevated above the base flood elevation, with waterproofing systems integrated into the foundation and slab edges. Passive flood protection measures included concrete knee walls, deployable floodgates, and sealed utility penetrations. Drainage systems with check valves and stormwater retention tanks were installed to manage runoff and reduce combined sewer overflow risk during extreme weather events. The residential portion of Bronx Point was constructed using a reinforced concrete frame. The structure consisted of shear walls and flat slab construction to maximize ceiling height and accommodate varied unit layouts. Formwork systems allowed rapid cycle times, with daily concrete placements coordinated alongside rebar and conduit installation. The tower was capped with mechanical bulkheads and roof-level amenities constructed using lightweight steel framing. The facade utilized a combination of brick masonry, metal panels, and punched window systems, referencing local architectural language while maintaining energy performance. Exterior insulation and air barrier systems were installed behind cladding to meet thermal efficiency requirements. Window systems incorporated low emissivity glass and thermally broken frames, enhancing insulation and reducing solar heat gain. Mechanical, electrical, and plumbing systems were zoned by core risers, with rooftop air handlers and energy recovery units providing ventilation and conditioning. High-efficiency condensing boilers supplied domestic hot water, while water-saving fixtures and submeters promoted conservation. Electrical infrastructure included LED lighting, solar-ready provisions, and smart metering. Fire protection systems included sprinkler and standpipe networks tied into a central fire command station. A major feature of the development was the inclusion of the Universal Hip Hop Museum, constructed within a large ground-floor volume. This space required long-span steel framing, acoustic isolation, and specialized MEP systems for exhibition climate control. Adjacent public plazas and waterfront esplanades were constructed with pile-supported decks, landscaping, and custom lighting. The entire site was knit together through resilient design principles, providing both community utility and urban resilience. Bronx Point stands as a model of integrated, equitable, and sustainable development in a historically underserved part of New York City.